Hello and welcome to a video on BJT bias structures. So in a previous video we looked at the currents and voltages around the transistor, and now we need to focus on how to switch on a BJT and the equations how to do this. Just there is a lot of methods how to to BJT a BJT lol to switch on a BJT. Alright, so we are going to look at a few methods. This is not everything that's available. These are some of the basics, and then one or two more complex methods and methods that works quite well. But we will be starting off with a bad example, then meandering into better methods, and then there's another bad example, and then something better once again. Okay, so there will be a lot of Kirchhoff's voltage laws going on in this video. If you're not comfortable with the currents in and around a transistor yet, I would suggest that you go and watch video 1 and get comfortable with the bias currents of a transistor or the various currents, and then watch this video. It might take a while to work through this. It's going to be a long video, but I will tag each and every one of the bias structures in the YouTube video. For the people downloading it, I will put the timestamps on the site, so you can skip through to whichever one you want to look at. And after each one of these, we will be doing a simulation where I can just show you the end result. So there will be the derivation example, which will contain design. So there might be some design equations around it or typical methods that it's done, and then some simulation. Okay, so we're going to look at single rail and dual rail a bit. And let's start with the base bias. So the base bias is basically just a resistor added to the base of our transistor. And we are going to look at the NPN case, the PNP case, and then the positive rail and the negative rail case. Later on, I will move away from showing the negative rail method because it becomes tedious in the same thing. And we just need to realize that first. And the PNP and NPN kind of reacts the same. It's just the positioning of resistors and the direction of current flow, which changes a bit, so you need to cater for that in the end. So the first bias will be all 4 cases, and then it will start to decrease as we move along. Right. So the NPN transistor, we add a resistor to the base. Okay, this creates from VCC a path into our transistor out the emitter towards ground. Okay, so that is how our current will be flowing. Same with our collector resistor. It will flow into the transistor and out at the emitter. So those are also the equations that we can set up. We can set up one from VCC to ground. So base current multiplied by resistor 2 plus VBE would be our rail voltage. And our rail voltage would also be equal to our collector current times resistor 1 plus our VCE value. So this is the simplest bias method around, but it is not the best. Okay, so we can take our first first loop here, and we have a base current, and we can rewrite it to contain our collector current in it. So we can get our base alone. So VCC minus VBE divided by resistor 2, or our base resistor, and then add this equation in, and we will have our collector current as a function of our rail voltages minus our VBE over resistor 2 multiplied by beta. Beta doesn't cancel here, it stands outside. So this is very dependent on our beta value. If your beta value changes a little bit, this entire bias current IC will change. Okay, so that is why this base bias method is not used a lot. It's not very stable. Right, here is the second equation I spoke about, and you can use these to design base bias. Right, for the negative version, current will flow from a higher potential to a lower potential. So if you were to use a negative rail with a ground up there, this will react exactly the same. The only change that you'll notice is that we are working with minus VEE instead of VCC. So VEE is a negative voltage, so minus 10 times the negative is just 10 again. Okay, so everything will work out exactly the same for both cases. Just so long as the current can flow in the right direction through your transistor, it will work. Alright, so there is two examples. They will end up with exactly the same results. I'm just going to look at the one. So the first one is related to this figure, and the second one is related to this figure right here. So let's say we have a rail voltage of 10 volt. Let's use a beta value of 200. And we are told, or we found, that we need to design for a collector current of 1 milliampere and a VCE voltage of 5 volts. Okay, I'm going to quickly go back. If you're new to this, you always try to have a value across this resistor and the voltage drop across the transistor to be equal to one another. That is for when you're building amplifiers, so that you can have maximum swing potential for your transistor. Okay, so it's a design consideration to have these two at the same voltage, have the same drop across them. Okay, so that brings us to designing VCE being VCC over 2. Right, so that is where this 5 volt design comes from. Now we need to find the resistor 1 and resistor 2, and let's assume our transistor switches on at 0.7 volts. In certain designs, it is best to go and calculate this value exactly, especially if a transistor is a bit on the twitchy side. Here we have beta dependency, so it's not going to really matter that much. And VCC is much larger than VBE. So in the end of the day, this value is going to be noise for our VCC. So it won't have a large influence on the collector current in this equation, but the change in beta will have a large influence. Right. So on to the design. VCC is 10 volts. We have to design for 1 milliampere. VCE is half of our VCC, 5 volts. And we only have resistor 1 left. That would work out on 5 kilo ohms. And the closest E12 is 4.7 Ks. So that's our first resistor designed. Our second one is just to apply this equation directly. 1 milliampere is the 200 beta 10 minus 0.7 over resistor 2. And this will work out on a very large resistor value. It's one of the other problems with base bias is if you need to apply biases on chip, for example, 1.8 mega ohms is quite large and not really that possible. So you will never see a base bias on chip, but in a circuit it is quite possible. If you look to this side, you will see exactly the same values that comes out. Right, so that's our first designs for NPNs. Let's have a look at the PNPs and then we can jump into the simulations. So for our PNP device, we need a current path through our transistor like that. So the base current flows out. So we need to go from VCC to ground, and the rest of the current flows through the collector like that. So it flows out of the collector and not into the collector. So we can set up new equations, and you will find that this works out on exactly the same equation as the previous problem. VCC minus VEB, so not VBE anymore, still beta dependent, and that's to calculate this resistor. And for resistor 3, we will end up with the same equations if we use Kirchhoff. Again, with the negative rail version, and you will find a PNP more likely in this negative rail configuration rather than the NPN that we did earlier, because the ground is a higher potential than a negative value, so our currents will flow correctly through our transistor. Okay, so doing example, same parameters as the previous one. Our resistors work out on exactly the same values. Okay, so you might think again that it's tedious that I show you the negative rail case and the positive rail case, NPN and PNP. Okay, because they work out on the same values. Right, that is to put your mind at ease that when I do a PNP and just apply a formula quickly, that they work the same. There is a couple of biases where they are not exactly the same, but we will get to them in a short while. Okay, so I'm going to open simulation on the NPNs and then on the PNPs and quickly show you. Right, here we have our dual rail setup. So VCC for our positive rail, VEE is for our negative rail. I decided to go over 2N quad 2 for our transistor. It has a beta value of 200. And if we run our simulation, we will see that there is a very small amount of current flowing in the base here. It should be about 5 microamps. Yes. And in our collector here, we have a little bit more than 1 milliamp. Okay, that is due to our choice of E12 resistors. If this was 1.86, that will start to move closer to 1 milliampere. Okay, also this we calculated as 5K originally. Right, so the bias here is extremely sensitive to the change in this resistor as well. So if you can't choose your resistor exactly, your bias will be off. Then your bias will also change for temperature changes, changes in the beta value, etc. So can get kind of a mess at some point. But in any case, here is our bias with a negative rail, and we end up to have 1 milliampere flowing in this branch as well, or approximately 1 milliampere. Okay, everything changes with the choices of components. Everything changes when you actually buy components, and they have tolerances. So using approximations by times or certain approximations is not a problem. You're not always going to have to work with exact values. You can't. There is too many variables and too many things that is dependent that it does not really matter. I will show you when approximation, certain circumstances, approximation is a bad idea, although they can be used when the conditions is right. Let me open the PNP simulation. All right, here is our PNP, and if we run it, there's approximately 1 milliampere, there's approximately 1 milliampere, and I decided to use the 2N3906. People will suggest a different transistor online to use in conjunction with the 2N quad 2, but the beta value of this transistor is 200, the same as the quad 2. I think people will typically suggest, I think it's this one just at the top here, and its beta value is about 50 higher. So I usually go with this one down here, which is much more of a really positive transistor to the 2N quad 2. Okay, so in any case, they work out quite the same as the previous two transistors. So let's continue on with the presentation. Right, this brings us to the differences or the observations on the base bias. And the base bias is a very simple solution. It's just one resistor you slap in and the transistor should be on. But the problems are your collector current will be unstable, okay, because it's dependent on beta very much. Here we can see it. And our beta value might vary over a large range for the transistor that's being selected or temperature. The base bias, you are also at risk for thermal runaway. Thermal runaway is when the transistor starts to heat. The collector current can flow more freely because the electrons of the element is flowing through is hot. So more electrons will start to flow, which means increase in collector current. That will heat the transistor even more, and it will get out of hand, and the transistor will burn out. There is no way to protect the transistor from the collector current actually running away. Okay, so to cater for thermal runaway, you need some form of feedback to keep the transistor under control, or have a beta value under control as well. You will see that those two typically goes hand in hand. Okay, lastly, this method you need a very large resistor, and also this method is rarely used because of all these negative points mentioned here. The base bias can be used in conjunction with some other methods, like when you have a current source employed or some other circuits. Okay, but we're not going to delve deeply into those in this video. Right. The next case that we have is the collector feedback bias. Okay, so resistor 1 is again on the output, and we have this resistor placed in here from the collector terminal to the base. Right, so current can flow into our transistor, and the current will also split, flow into our transistor and out on the other side. So the current flowing in resistor 1 is the same as the emitter current, technically, because the collector current is only located after that point. So if your beta value is quite high, I see I used collector current from the beginning here and not emitter current, but the assumption is that the beta value is quite high and the collector and emitter current is very similar. Okay, so to set up equations, VCC is ICR1 plus VCE, and VCC is also ICR1 plus IBR2 plus VBE right here. So we have two equations. So one only has two variables in, and the other has three variables in. And we can also see that our collector voltage is equal to our VCE voltage, which is also equal to this part here at the back. So there is a couple of equations that you can write down. Okay, so VCC equal to ICR1 plus VCE is your first equation. That's the one where we are going to deal with the Q point and the selected collector current to find our emitter resistor. Next, we used this third equation here to find our collector current. So VCC is ICR1 plus IBR2 plus VBE. So if we get IB alone, so we need to plug this in here, we end up with VCC minus VBE over beta times R1 plus R2. Converting it to a collector current, we multiply this entire equation with beta. So our beta on top and betas at the bottom can cancel out. So we have R1 plus R2 over beta at the bottom. So the effect of beta becomes less in these equations. So if R1 is much greater than R2 over beta, our beta dependency will be gone. Okay, R2 is also a feedback resistor. Right, and we know that feedback is there to cancel out nonlinearities and distortions and dependencies like this. Right, for the negative case, only change that we have is VCC changes to a minus VEE. Exactly the same derivation that we had. Right, so let's do example. Just going to focus on the one side again. You can observe that the other side is exactly the same. And again, we are going to design every time for kind of the same parameters. So you can see that there is many ways to do the same thing and actually observe the differences and or similarities in components. So again, with this, we want the voltage drop here and the voltage drop here to be the same. And we end up again with 4.7 kilo ohms. Calculating resistor 2's value since we already have resistor 1's value, we find resistor 2 is 920 kilo ohms and the closest value is 1 mega ohm. So this feedback resistor is still a very large value. Right, but we are closer to beta independency. So 1 mega ohm divided by 200, this term will still have a significant effect in our bias here. Okay, but there is hope that we can actually start to eliminate our beta in one or another way. Okay, let's have a look at the PNP case. The PNP case, current will come into the top, flow through this resistor and join at the collector. So again, we end up with having the same equations. This equation is very similar to this one right here. I just use different resistor numbers, but they are the same and the resistors are in the same positions. So the NPN and the PNP biasing here for the positive case and the negative case is exactly the same. Okay. Whenever you hit a case where you don't know the biasing equation like this, just stop, draw up all the Kirchhoff's loops that you can, find out where you can replace IBs or ICs, isolated that you only have one of them. Okay, only ICs or IBs or IEs in your equation, and then get everything on the other side. If you multiply IB with a beta, you have IC. If you multiply IB with beta plus 1, you have IE. Okay, so always try and aim to get to this equation right here. And we always try to get to the collector current because the collector current will be one of the currents that we are interested in for designing and when we are modeling a amplifier. Okay, so it's for designing and modeling and analysis. The collector current is quite important to get out. Right, following the design rules that we have set out for these particular scenarios will also help in the design process. Okay, so I'm using it correctly here so that it can start to imprint on what we are typically looking for. Right. So the observations here before I go to the simulations is we have a lower chance of thermal runaway. That's because our beta value is not a large role playing or a large role player in this equation. It is also still a very easy bias solution. It is much more stable than the base bias. We still require a larger resistor, and if we are interested in amplifiers, having a feedback resistor like this, it will load our inputs and outputs. So it has a loading effect on our transistor. So it's something you need to keep in mind. Right. Then it will also reduce the gain of your amplifier when you do this. And one that I haven't put here, it is that it will make calculating the frequency response of amplifier a little bit more difficult because you need to use Miller and all kinds of stuff. So this kind of feedback bias is tedious in certain regards, but it's a very easy solution. Okay, let's look at some simulations. Right, here is our NPN circuits, positive rail, negative rail. Let's run it. 1 milliampere, and you can see this is much closer to the value that we designed for. So that is due to this value being divided by beta is not as dependent. It's a bit more robust, if I can put it that way. So this will bring you much closer to actually having the current you designed for, and it's a little bit more stable. Let's open up the P. Okay, here's our PNPs. Let's run them, and voila, 1 milliampere, 1 milliampere, exactly the same components as our NPNs. Right, on to our next biasing method. Next up is our emitter bias. Right, so we have some voltage source through a resistor connected to our base so that we can have a current flowing in there. We have some resistor on our emitter, and we have a resistor on our collector. Typically, as always, we want the voltage drops across resistor 1 and the voltage drop across the transistor to be the same. There is now a third party here, and we always want these two to be the same. Okay, always. This one here at the bottom does not need to be the same as the two on top. Okay, it is not a requirement. The common method is to have all three of them be the same. Okay, but be careful. This is not always the requirement. And if I remember correctly, one of the examples we will design for a different emitter voltage. Okay, so always try to keep the collector and the VCE the same, but the emitter can be a different value. I can't stress this enough. I've seen it a million times when people assume this when it's explicitly stated that the emitter voltage is not the same as the IC or RC and VCE values. Okay, very common mistake. A lot of people failed at designs due to that. Right, or to reach specifications. Now, here we have again two Kirchhoff loops. Let's clear everything. Okay, so the first is to go from ground to ground here. So we have VBB is IBR2 plus VBE plus IER3. And the second one is from VCC downwards to the ground. It is the same as this voltage source here. So VCC is ICR1 plus VCE plus IER3. So this resistor is present in both equations. VBB is on the input side. VCE is on the output side. So having this in both terms indicates that R3 here is actually a feedback resistor. Okay, so some of the voltage on this output side is fed back to the input side, which typically has a stabilizing effect in a circuit. Okay, so we are going to work first with this VBB term, and we are going to try to make everything to be IBs. So we have IBR2 and beta plus 1 IBR3, which is this emitter current that we had originally. If we get the voltages alone and IB alone, we end up with VBB minus VBE divided by beta plus 1 R3 plus R2. Right. So if we multiply by beta, we can see something interesting happen. Beta plus 1 and beta kind of approaches the same value if beta is a large value, right? Or the case when IC is approximately equal to IE. So if we divide top and bottom by beta, this term will cancel out. Well, close. So that's why we use the approximate. So, and we will end up with VBB minus VBE over R3 plus R2 over beta. And plugging in this IC approximately equal to IE term in the top one, we will find R1 plus R3 multiplied by IC plus this VCE over here. Okay, so these two are our design equations. Right, so let's go into an example. We'll get to the note in a moment. So let's say our VCC is 15 volts. We design for 1 milliampere current. We need to ensure that our VBB is larger than BB. So if we pick this 6 volts, it should be larger than our VB value, because VB is the 5 volt drop over here plus 0.7 is 5.7. So there should be 0.3 volts left here towards our VBB over there. Right, then I said that we need to make the normal assumption because no information was given. I did the different VE on another example elsewhere. Okay, anyways, moving on. If we have our three voltages the same, we have VCC over 3, 5 volts. R1 and R3 should be the same resistor value at 4.7 kilo ohms. Then we can calculate our base voltage. And we assume our base voltage. No, we don't assume our base voltage, excuse me. We just need to check. So our emitter voltage plus our VB is 4.7 from this 4.7K times 1 milliampere will get us to 5.4 volts, which is less than 6. So this kind of bias with VBB being 6 volts will actually work because the current can flow into the transistor. Remember, higher potential towards a lower potential. And we can now use this equation right here. So 1 milliampere should be 6 minus 0.7 divided by 4.7 kilo ohms plus our resistor 2 divided by 200. And that's 120 kilo ohms. 120 kilo ohms divided by 200 is a much smaller value than we saw in the previous problem when it was 1 mega ohm, right? So here is much more stabilizing going on than the previous problem. This is less beta dependent already. Right. So let's take some notes on our equation of VBB and VBE here. If resistor 3 is much larger than R2 over beta, this term much smaller than this we can throw it away. And if VBE is much smaller than VBB, we can also throw that away. And our equation will reduce to VBB over R3. this is just approximation. You can't always use this. Okay, so 120k divided by 200 gives us 600 ohms. So just with this first approximation here, we can approximate our current at 1.1277 milliamps. So that is very much less dependent on our beta value already. Okay, so our collector current will be more stable. Although the second approximation is not a good one to make because this will start to increase this value quite a lot, but it is still fairly accurate. Okay, so you can approximate your collector current by taking VBB, dividing it by the emitter resistor. Okay, but remember, approximations are based on assumptions. So always check your assumptions, please. If the assumption is right, the approximation will be accurate. If the assumption is wrong, the approximation will be a big fail. But you will sometimes see some of these equations just used, and you won't see the approximation anywhere on the page that you're looking at. Okay, it's always best to stick with the bigger equations than the small ones, depending on a lot of approximations. Right, so that is the NPN. This is the negative case. In the negative case, you will see that there is a little bit more going on in the equation down here. So you can pause the video and work through this bias right here and see if you get to the same result. But the negative rail case is not exactly the same as the positive case. And also note that VBB has been inverted as well to cater for our VEE value right here. Right, so the currents will flow correctly. This needs to be a negative voltage as well for it to work. So you can pause it and work through this, and I will show you in the simulations that with these equations we end up with the same kind of collector current. So the example on this one, you'll note that we have a different resistor value in the end, and our approximations falls very short. So if you try to make these approximations with a negative one, you will end up with 2 milliamperes instead of a 1.025 milliamps. Okay, so the approximation does not work for our single rail emitter bias with a negative rail. Okay, you can work through this one on your own time. I will never give this one in a test. It is very tedious, but it is good practice for Kirchhoff's laws and how to find the currents and calculate a bias structure. Okay. Next, this is a more practical approach for our emitter bias. Okay, and instead of having a negative source, we can connect our base to our collector voltage. Okay, so this is a emitter bias using a collector feedback. So technically we have double feedback on this problem. And this is a more typical implementation, which is a bit more stable than any of the other implementations. So again, we have a path going through the back here and down, and a path in front, and we can write down all the equations. And now you'll see that we have these two terms in both. Okay, so we have a lot of feedback in here. Going through the motions, and for this one I used the VCC of the second one over here, getting everything alone and our base current alone. We will find that our VCC minus VBE divided by R1 plus R3 plus R2 over beta is our approximation for our collector current. With an extra resistor added, we have a much larger chance of having a larger value than a resistor 2 over beta. So it can cancel this term out easy, and we have a much more stable collector current. For the negative one, you guessed it, the only difference is the minus VEE. So where with the voltage sources connected, they yield different results. For the collector connected, they yield similar results. Okay, looking at the example, finding all three resistors. Again, resistor 1 and resistor 3 will work out at 4.7K with our VCC over 3 assumption. And just to show, if we calculate our new VBB value, it will be at 11 volts, and our VB value will be at 5.4 volts. So VBB will always be larger than our V value in this configuration. Okay, so this will always be on, it will always work no matter what you do. Right. So for the collector current, we already have our two resistors, and R2 over beta will work out at 1 mega ohm here. So this is kind of a mix between the emitter bias and the collector feedback. And the collector feedback, our resistor 2 was a very large value to begin with. Okay, so if we look here, again, we can't make our approximations for our resistors because they are not quite large enough. But the one that you can typically make here is VCC much larger than VBE, because this is 15, that's 0.7. So this part of approximation will work out quite fine, but in this case, this one is not valid at all. Okay, because it's kind of a stretch from the one to the other. Okay, so some observations. It's more stable with regard to our beta value. It will be more stable over a large temperature range. We don't need extra source if we use the self-bias method, so the collector feedback. And we have two feedback resistors in this option. Okay, then as a note from here on, you noted that I didn't do the P&P, and from here on forward I will only do P&P if there is a case where the derivation will differ, and I won't do the negative cases anymore because from here on forward they will typically always be the same as the positive rail case. Okay, So we're only going to focus on positive rail and NPN mostly. Okay, let's jump over to the simulations for this emitter bias, and let's check out our currents. Okay, so here we have our first two setups, one with our extra source, one with our source inverted and negative rail, and then the two calculations, positive and negative rail, with our feedback setup. So you can see that we have values that we calculated. So if we run this, there's 1 milliampere, there's 1 milliampere, approximately 1 milli, and these two are exactly on top of one another, and they are pretty damn precise. Okay, that's at 10 volts, that's at roughly 5, minus 5, minus 10, negative rail, 10, 5, minus 5 roughly, and 10. So everything we designed for is going on in these circuits. Okay, however, we didn't calculate the PNPs. I will still show you the PNPs, and we will have roughly the same values. Alright, with our PNP devices, the only thing that you should notice is that it was 120 kilo ohms for this side in the previous problem, and 680 for this one in the previous problem. So the two resistors just flipped, but the feedback kinds have exactly the same values. Okay, so running them, 1 milliampere, around 1 milliampere, 1 milliampere, and this one lies on top of that one. So these are fairly close to one another. Right, on to our next biasing method. Now, here is our first iteration of the voltage divider bias. Okay, you're going to have the same scenarios for NPN and PNP. Just here we want the VBE sitting across R2 at the bottom, and VEB is on the top here. So don't go and when you have to design for a PNP design on the wrong side of the transistor. Okay, the reason why I started with the voltage divider without having an emitter resistor here is to show you that having a voltage divider, just plain straightforward, is no good. Okay, so plain and simple again, VCC is ICR1 plus VCE, and we can use this branch here at the back with a small amount of current that needs to flow into the base. Okay, if the current flowing here at the back is much greater than the amount flowing into the base, we can kind of ignore the base value. Okay, because there is enough current flowing and the base is only going to steal a little bit to switch on the transistor. Okay, but if we are analyzing a circuit, we are going to go through different steps than actually designing a circuit. Okay, if you can analyze a circuit properly, you should be able to design a circuit properly. But don't mix up design rules when you're trying to analyze a circuit. Okay, some of the design rules is or was maybe not used when designing a circuit. So if you need to analyze it, don't assume that the person who designed it was using the design rules. It's just a little bit of a warning. Okay, but analysis and design are connected to one another, but they can also stand very loose from one another. Right, so to analyze this voltage divider bias, we first need to find this point here, VBB. Okay, and that is not the base voltage. Okay, we convert these two resistors into a Thevenin source and a Thevenin resistance. So basically we are placing a voltage source with the extra resistor in here. Kind of like this setup that we have just done, just without this resistor present. Okay, so we are replacing a source and a resistor in this problem. So we call that VBB is VCC times R2 over the sum of the two. Okay, so this will feature in your design equations, but it will look different. And the Thevenin resistance is just a parallel combination of the two resistors. Then we can write VBB is IB RBB plus VBE. Okay, so to get to our base current, we need to do the Thevenin. So the base current is VBB minus VBE over RBB multiplied by beta, we get our collector current. Beta does not cancel in this case, so there is no beta stability when we are using a voltage divider without the emitter resistor. Okay, so that is where the warning lies, that this voltage divider bias is not a good idea. This is as good as using a base bias. The nice thing here is you get to choose your input impedance and you get to use lower resistor values. That's all upside that there is about this voltage divider bias. Okay, when designing we can use the rule of thumb, and that is IB is approximately 0, and if our beta is much greater than 10, so a beta of 100 again will be fine, we can assume a current of IC over 10, so the current on this side divided by 10 is the current flowing on that side, ignoring the base current. Okay, that is only if this rule is true, otherwise you have to work with your beta value in your equations. Okay, so resistor 2 plus resistor 3 should be our VCC value divided by I1. So the current we just calculated will give us our VCC value, and resistor 2 should be approximately VBE over I1 right there. Okay, so there should be 0.7 volts drop across here and 0.7 volts drop across there. Okay, now these equations are based off a lot of assumptions. So if we're designing, so we're going with a normal VCE of 5 volts, 1 milliampere design. I should remove that R3. No, there is R3. Ignore me. Anyways, we will find that with 1 milliampere divided by 10 is 100 microamperes. 10 volts divided by that is 100 kilo ohms. So the total resistance here at the back should be 100 kilo ohms. Going with 0.7 over I1 will give us 7 kilo ohms. Closest E12 value is 6.8. R3 here is 90, should be 93 kilo ohms. My bad, I was working with a different VBE value initially. Sorry, I was working with 0.6, not 0.7. But both of them are between E12 values. So that's between 100 kilo ohms and 82 kilo ohms. 93K would be the best option to get our ideal IC value. Because we can see that this equation will be very heavily dependent on our R2 value. Okay, so R2 needs to be very accurate. R3 with that with our voltage divider should be accurate as well. Right, so if we go and calculate using these resistors, we find that our VBB value is 0.766, which is larger than 0.7. We assumed 0.7. RBB is 6.28. And IC would be 2.1 milliamperes. That's using an 82K instead of a 93 kilo ohms. Using 100 kilo ohms, we get to a value of 0.637, which is less than 0.7. So we are sitting in a bit of a pickle here. The one resistor will give us a larger collector current. The other resistor will give us a smaller current. The transistor will still be on because this is still above 0.5 volts. Okay, so this says that we can't assume a VBE value when we're using this voltage divider bias. So we need to calculate it using the equations from video 1. That exponential equation, we need to calculate it using that. Okay, or else this voltage divider will be extremely unpredictable. Okay, let's jump into a simulation of this and then we go to the voltage divider when it's done properly. So here I have it set up with the resistor free here with the 93Ks, the 82K and the 100K. So that's the choice and that's the ideal value. So let's run this. So we will see that with a 93K we are very close to the 1 milliampere. But for the one it goes up to 2.1 milliamps and the other one it actually drops considerably. Because for the 100K this transistor is switching off already. For the 82Ks it is biased with a larger voltage here, so there's more current flowing. Okay, so without the emitter resistor, this is very dependent on our resistor choices here at the back. There is our different VBE values. So you can see that there is not much difference between them, but it actually makes a huge difference in the collector current. This is about 1 thermal voltage, that's about 1 thermal voltage away. Okay, so it actually makes a huge difference. Let me show you the simulation of the PNPs. Alright, here I have done exactly the same with a PNP. You'll see that the values ended up to be the same. Just the 6.8 is now here at the top and not the bottom anymore because the voltage we are interested in is sitting up at the top here. So if we run this, we have exactly the same results. Switching off close to 1 milliampere, 2.1 milliampere, just like that. So this biasing scheme is a big no-no. It's very dependent on the resistor value. So even if you get something that's close, a resistor that's close in value, you will have issues with your tolerances. This is still unstable for different beta values. Okay, so let's jump into a proper base voltage divider bias. Okay, so the proper way is to add an additional emitter resistor into the mix. Okay, for both NPN and PNP. Okay, so we can use the same Thevenin equivalence when figuring out VBB And then when you're calculating or doing the loop down here, you will just have extra term with the emitter current, and again you have the same result in the loop over VCC and the collector. So we are having feedback again, and feedback means that we have some form of stabilization happening. Right, getting IB alone again, we have VBB minus VBE over RBB plus beta plus 1 times R2, because this is from the emitter resistor. And if we multiply by beta for our IC value, we will see that if we start to cancel values out, we are left with RBB over beta plus R2, okay, or the emitter resistor. So again, if this emitter resistor is much larger than this term, it can cancel. And using the rule of thumb, getting this RBB, it can be a fairly low value. And if we have a large beta value for our transistor, this bias will almost be entirely dependent on our resistor 2 choice. Right, so for noting, as I said, if RBB over beta is much smaller than R2, then we will end up having our emitter voltage across our resistor 2 value as our collector current choice. Okay, collector current approximately equal to our emitter current with large beta values. So, rule of thumb again, if beta is much larger than 10, we can say that we can calculate I1, get resistor 3 and 4, use this equation to get resistor 2, and with our VCE value and our choices of VCE, we can find our resistor 1 value. Okay, so putting it in an example, using a VCC of 15 volts, find all 4 resistor bias for 1 milliampere, R1 and R2 with the assumption of VCC over 3 would be 4.7 kilo ohms. Resistor 3 and 4, 100 kilo ohms, just like the previous example. And now we have to find a base voltage. Now the base voltage is our emitter voltage plus our VBE voltage, and that's 5.4 volts. And we equate this to our VBB value. Okay, so we are assuming that our VBB and our base voltage is exactly the same voltage when we're designing. Okay, since we are working with tolerances in the end, and this one has bias stabilization built in, and our bias is actually dependent on our resistor 2 value here, we will have a stable bias. Okay, so we can equate this to this 5.4 volts. It won't matter that much. And we will get a resistor 3 at 68 kilo ohms. So we are solving this equation and this equation simultaneously. So basically you can just plug in 100 kilo ohms here at the bottom and you find resistor 4. And we get 68 and 39 kilo ohms. You'll always see that there is roughly a 2/3 and a third kind of ratio with this VCC over 3 design for our base resistors. Okay, so that is design 1. Design 2, I said that use emitter value of 3 volts. Okay, so emitter value of 3 volts, the emitter current or the collector current, assuming that they are the same with a large beta value, is VE over R2. Find our resistor 2 value as 3 kilo ohms, and that translates to 3.3 kilo ohms as E12. So that's the first resistor value. You just use the stabilization equation that we have just derived. And then you can find new values for R1. So VCE should be equal to ICR1. See, I'm not using VCC over 3 on this one because there was a given emitter value. And that ends up to be 6 volts. So 6 kilo ohms, closest value 6.8 or 5.6. I'm just going to go with 6.8 kilo ohms. And where is our second resistor calculated? Then we go through the same rigmarole as this side. We will have a slight difference because our VB voltage will be different, because VE is now 3 volts or 3.3 volts with the 3.3 kilo ohms, plus VB is at 4 volts. So now we're just designing for 4 volts instead of 5.4. Solve these two simultaneously. Get 73.3 kilo ohms and 26.7 kilo ohms, and that is 27 Ks and 68 K E12s. So let's put this in a simulator and see what pops out. So here is our two solutions implemented. Let's run it. Here is our emitter voltage at, it is less than 5, but we use the 4.7K, so that is close to our design values. There is almost 1 milliampere flowing in there. Same here at the top, minus the base, but 5 microamps. So we did reach our specifications, all 3 of them here. And you'll see that this is a little bit more than the current we designed for, but that is due to our choices of resistors with the E12s. And that is close to 5.4. Okay, this current is very close to 1 milliampere, and that is due to this emitter resistor right here. Our resistors are much smaller than any of the other problems that we did. So that is why the voltage divider is so popular, and it is independent of beta. Alright, our second solution, we chose this to be 3.3 volts in the end with a 3.3K, that's slightly higher. The current flowing here is 1.06 milliamperes, still fairly close. And we have different resistors here. Okay, that is very close to the 4 volts that we designed for. Okay, so two very different solutions. This one using VCC over 3, this one using a different emitter value, but we can clearly see that our stabilization comes from our emitter resistor. Okay, so let's draw some conclusions. So this is very stable with regard to beta due to it cancelling out almost everywhere. It is stable over a large range of temperatures. The voltage divider bias only influences the input impedance, and it uses feedback on to stabilize the bias. So another avenue opens here is we can manipulate the input impedance with these two resistors But to do that, we usually forget about the rule of thumb. As long as our beta value or enough current can flow into our base, our transistor can switch on. Okay, so this is just a plain design rule for when you don't know what to do with the input and want it as high as possible. If you have a specific input impedance, you can forget about this rule. There is a different method to do that, but we will discuss that more when we get to designing actual amplifiers. Okay, these are more related to the DC bias. Okay, next we can bias our circuits using current sources. Okay, ideal current source has infinite impedance internally, and it will draw a certain amount of current from your circuit. This is the best way to bias a transistor. So we can take our previous configuration and just slap in a current source. Okay, and what a current source looks like in real life, it is just a double transistor configuration like this. And how it works is quite simple. The VBE voltage here is exactly the same as the VBE voltage there. Okay, so if this transistor is biased at a certain amount of current, it will give its VBE to this transistor, and it wants to sync the same current that is seen on the other side. This is called a current mirror. It mirrors what it sees on the other side. The setup to get the current flowing is quite simple. You diode connect the transistor. So this transistor will always be in an on state. Okay, because VCE will always be equal to VBE. So this transistor is always active. So you can take VCC and subtract 0.7 volts because VBE is connected to this point, and divide it by the collector current that you want, and you get a resistor value. In this case, about 15 kilo ohms. So 1 milliampere will flow there, which will want to sink 1 milliampere there. A small amount of base current will enter, and this transistor will be biased at 1 milliampere. Okay, and typically an ideal current source has an infinite impedance. A current mirror like this uses the output impedance of this transistor, which is the early voltage divided by the collector current. This is more something that we will use in amplifier design. Some later videos on that. So this is a simple current source bias. Okay, so I will quickly show you these in simulation. The PNP variant, it must just come from the top. So this is actual current source. One at the bottom is technically called the current sink. And the PNPs is connected in the same configuration as the NPNs. Right, let me show you how this looks in simulation. Right, we used the same components as the previous problem in the simulation, and just the emitter resistor was replaced with a current source. So the voltage drop across here should be the same as our previous design. And if we check the values after running the simulation, that is spot on 1 milliampere with the current source. You zoom in, there will be a little bit of difference, 5 micro amp difference. So only the bias current extra, right? Here we have the voltages that we designed for. And if we look on this side where we replace this current source with the actual circuit, there is something a little bit less than 1 milliampere due to our component choice of 15 kilo ohms flowing here. We check this transistor. The emitter current flowing out is 1 milliampere. The current flowing up here is roughly 1 milliampere. So if you can use a current source, this is the best way to bias a transistor, and it will open up a whole lot of new avenues for you when designing amplifiers. It will make amplifier design really simple if you can just build a current source like this. Okay, let's check out the PNP type. Okay, here we have a PNP. Let's run it. Almost 1 milliampere. Almost 1 milliampere. 1 millivar. And it is working. Okay, so use current sources if you can. Okay, let's go over to the dual rail problems. Right. If it's possible to use dual rails in your amplifier designs, it also makes life easier. If you're using op amps, typically you will have dual rails. I know that you have single rail op amps, but dual rail implementation also improves your lifestyle. So the NPN and PNP will in general work out in the same way. And there is a lot of similarities between the dual rail emitter bias and the single rail emitter bias. Just the VBB value that we had is now just a ground. Okay, so ground is the higher potential between here and VEE, because that's a negative voltage. So current will still flow into the transistor out of ground, through the transistor and through this resistor here, from a higher to a lower potential. Okay, and when VCC is a higher potential, VEE is a lower potential, and our current will still be flowing in that direction. So, same goes for our PNP implementation. Right, so the equations will work out pretty much the same. So we are just going to look at the NPN implementation. So we are interested in the loop down here. Right. So 0 from our ground is IBR2 plus VBE plus IER3 plus VEE. Okay, so just a simple loop. We know that VEE is a negative voltage. And if we get all our voltages alone and get everything to be base currents, we have minus VEE minus VBE. So this will change our voltage into a positive again in our calculations. Okay, minus 0.7, and we have our base values. Okay, converting to a collector current, that should be IC. Sorry. We can find the same relation that we found earlier on, that our emitter resistor plus our base resistor divided by beta here at the bottom. Minus VEE will be much greater than VBE. Okay, so VBE can be thrown away. If R3 is much greater than this term, we can throw it away and your collector current will be minus VEE over R3. That looks kind of familiar. That looks the same as what we had with the voltage divider bias in the previous problem. Okay, so if you want to do a design, there is some important things. First off is our VCE value. We have dual rails. Let's get rid of all this. Okay, so we want the voltage here and the voltage here to be the same. So that's VCC over 2. We don't use VCC over 3 here because we have an emitter value right there. Okay, so this bottom resistor and source will be responsible for our bias, right? And these top two will be responsible for our maximum swing. Resistor 2 will be will influence our input impedance and is basically just supplying a path into our transistor. Okay, so the voltage here at the emitter is best to choose it at a low value but a negative value, so minus 0.7, minus 1.4, there around. Right, so first thing, assume VCC over 2 for these two values only. Make your VEE something smaller than minus 1.4 volts, then you will always be safe. Everything will be on and functioning well. Okay, and meaning smaller is you can go to minus 2, minus 3, whatever. But if you take this too low, it will be eating into your VEE value and this bias becomes uncertain. Okay, so that's why I included a bit here with plus VE in this equation. So the design equations, resistor 3 is our negative supply plus the emitter voltage choice divided by the collector current we want. And resistor 2 should be around our emitter voltage minus our VBE divided by the collector over beta. The beta instability has no effect on this resistor. You can choose a resistor 2 as your heart desires as long as enough current can pass through that resistor into the BJT. Okay, so there is an equation where you can calculate it, which is a good value for it. But you can pretty much choose it anything and it will work. I will show you in the simulation. It will yield kind of the same values for the collector current. You will have offsets, but if you have an input capacitor on the input, the offsets is not going to matter that much. Right, so designing for emitter value of minus 1.4. Again, our VC is 5 volts. So resistor 1 is 4.7 Ks. Resistor 3 using this equation we find as 8.2 kilo ohms. So 8.6, roughly 8.2. And resistor 2 ideally 150 Ks if we want this minus 1.4 at our emitter voltage. So that's quite the easy design. There is 3 equations that you can just plain straightforward apply and it will pop out the results. Okay, so before we go to the simulation, this is a very stable method to bias a transistor. You can pick the input impedance of your amplifier with this. The emitter is responsible for the bias. The base is only a current path. So making adjustments to this kind of design with the dual rails is very, very easy. Every resistor has its purpose. So R2 is for input impedance and providing a bias path. R1 will have to do with a gain if we're building an amplifier and our VCE component. And resistor 3 is responsible for our bias current. Okay, so the purposes with this dual rail is kind of split, which makes life really easy for one of these designs. Okay, so let's jump over to a simulation. So here is our simulation with a 4.7K here for our VCE selection, the 8.2 for our current selection, and I've gone and placed various resistors in the position of R2, and you will see the effect that it has selecting different R2 values here. Okay, where 150 is kind of the best case scenario or our design parameters. So if we have a look at the current here, you can see that this is all very close to 1 milliampere like we designed. Even with this change in our resistor 2 value, our voltage here is around 5 volts. So we achieved our VCE value. And here is all the voltages. And you can see that all of them are much larger than minus 0.7. So 0.7 is the ideal point to choose it. And then you can even leave out R2 almost entirely. So that's the smaller the resistor values go. But in any case, this green one right here, if I remember correctly, that is our 150K. But these are fairly small values still. And the collector currents are all very close to 1 milliampere. Okay, so the dual rail is a very nice biasing method here with the emitter stabilization. Let's have a look at our PNP device. So here we have the same scenario. Let's run it. Almost all of these currents are close to 1 milliampere, even with a change in the resistor 2 value. The ideal would again be 150K. And that's it. This method is almost a carbon copy to the NPN device. Our PNPs and NPNs behave very similarly. So I urge you to stop being afraid of PNP devices. I know there's a lot of people that avoid them. They are very similar to the NPNs. And most people are afraid of dual rail. This is quite simple. This dual rail setup. It has a lot of advantages. Okay, on to the last problem, which is the current source method for the dual rail. For the dual rail with current sources, I decided just to have two images, one for the NPN and one for the PNP. So on the next slide. So the emitter resistor is again just replaced with a current source. So the mirror circuit again, but with dual rail, we don't have to take it to VCC. We can take it to ground because the current will be flowing up into this resistor towards the lowest voltage here, potential. Our VBE's values will be the same again, just as in the previous problem. Okay, so this just turned from grounds into VEEs, and this one turned from a VCC into a ground terminal. You can, however, take this to a VCC. You don't have to take it to ground. Then this resistor value here will just be a little bit larger to accommodate for a larger voltage drop across it. So you can bias a transistor, have a correct VCE value, right, half, be able to adjust the input impedance with 3 transistors and 3 resistors. This is the absolute best way to build an amplifier or bias a transistor. Building an amplifier with this is really easy. So yeah, the PNP version, emitter resistor replaced with current source, PNP devices up top, and you are done. So let's go over to the simulation of this, and then we will be finished with this video. I know it's quite a long one, but there is a lot of handy biasing information in this video. So I apologize, but it is good for you to do a lot of maths and actually learn about the current flows and the biasing and Kirchhoff. Right, so here is our deal rail with ideal current source and then one we built. I have for the one with ideal current source just added a bunch of different resistors so you can see how it reacts with a current source. So if we run it, we see that all of these are very close to 1 microampere. 1 milliampere. It is only a difference here in the decimals what occurs, even for a lot of base resistor values. Okay, you can see that you will still have the same kind of voltage drop differences that happens for different resistors. I included the 560 here, which is a huge change, and you can see that there is a very large change in the voltage on this point. But the voltage across here remains the same at 5 and 5, even with the big changes in the base resistor. So we can very easily adjust the input impedance for these, even with the current source. Okay, let's have a look at our own built one. That is almost 1 milliampere exactly. I have to zoom in quite far to find the difference. And we use the 10K here, and with the 10K we have minus 0.7 at this point. There is almost no current flowing into this transistor at the base side then, but there's a very small change in voltages. And there we have our biased transistor using a current source. Let's look at the PNP device. So here we have our PNP device set up, running the same kind of simulation. This current again doesn't differ by a lot. This perfect current source. The only difference is in the amount of current taken away here into the base. And they are very small changes. Okay, the voltage here, 0.7, 1.4, etc., etc., etc. So difference between the NPN and the PNP device is you're going to select the positive voltage and not the negative voltage for the emitter value. So point to note down. And again, the current source just coming from the top using VCC, and that is biased at 1 milliampere. 10k base resistor, 10k here with a current source to set our current. And that's another perfect bias. Okay, so that is it for biasing structures. Sorry about the long video. But yeah, I hope all of this helps a lot. And good luck when having to bias a transistor. And we will mix all of these methods in when we are doing actual amplifier design, and the current source, this one, the ideal, not the two transistor one, will feature a little bit more when we are doing actual BJT frequency response, just to make our problems easier. But now you understand what the current source actually does inside a transistor circuit. Thank you for watching, and see you in the next video.